Welcome to E-Pathashala lecture series for MArch students. The content here is sustainability and green building material. Under this, we are looking into the LCA and the components and the energy embodied energy in a part 2. So, we are looking mainly into the annual age of the lifespan of a building. Let us say 60 years of building life, and the construction used in this building. It can be a steel frame or beam or precast concrete slabs, or it can be a composite beams in the buildings or composite slabs combination. I repeat, it can be a composite beams or composite slabs in the buildings. It can be a on-site reinforced concrete frames and slabs. It can be a steel frame which has a combination of cellular beams and also a composite slabs. It can mean any varieties of concrete frames and precast concrete hollow core units. Among these 5 categories, the building may come under into any usages of frames or beams or slabs. The various building services options like natural ventilation and different mechanical systems for HVAC units, which again fully air conditioned building or semi partially air conditioned buildings or single component single usage of air conditioning, and hundreds of calculation which is involved in this combination of the analysis of the energy. So, life cycle embodied energy, analyzing or understanding the material value from cradle to grave and the energy which is used in terms of construction, production and also in terms of transportation. Now, look at the value in the graph. It has a scale from 0 to 25, which gives a value for a slim floor and composite floor and a reinforced concrete buildings and also cell beam buildings and also precast buildings. All these lies in a same value. It is like structurally sound and refurbishment in a greater extent. Now, life cycle embodied carbon dioxide graph chart, if you look at it. Similarly, it ranges from 0 to 2000 tons a kg of square meter emissions. Again, the various constructions typologies which is used in the buildings like slim floor, composite, reinforced, beam and precast, which differs more or less. The value lies similar for the 800, 400 to 800. We can look at the rest or refurbishment layer, which has a very slighter increase in terms of the graphical charts, and also in terms of refurbishment also it does not provide any kind of a greater difference in terms of emission of carbon dioxide, and generally it ranges for any typologies like 0 to 2000 kg of square meter emission of carbon dioxide. So, operational energy of a building to run the building in a well manner. Let us look at the examples, like it is a 4-story office building which is air conditioned building and has a mechanical supply, and dimension of the building is 48 meter by 13.5 meter, which is we need to calculate the value of the operation of the building in an average of 60 years, and look at the operational energy which is required for the building in terms of gigajoules and per square meter. All these slim floors, composite materials, reinforced concrete materials and cell beams or precast materials, which ranges of 0 to 35, it is nearly to the 40 range. All these operational energy is required for a maintenance of this building in a greater extent. If we need to operate this building in terms of composite beams and composite slabs and and a period of about 60 years, by natural ways it emits only 0 to 12 gigajoules per square meter. In a mechanical way, if you look at it, either it is a air conditioned or partially air conditioned or other ways, it comes under to the value of about 30 to 40 in a range of mechanical devices. Comparison between the electrical energy and the operational energy for the same 4-story office building in terms of size of 48 meter by 13.5 meter and a period of about 60 years. Y axis it gives the gigajoules per square meter in terms of operational energy and the electrical energies, and the x axis it gives the components. So, for electrical structures it is somewhere around 0 to 5, and electrical energy other things it's more than 5, and operational energy like lights which gives a value of about 30 to 40, and other HVAC usages also to an extent of about 35 to 40 it gives. In this way, we are understanding the difference lies between the embodied energy and the operational energy. The embodied energy, which includes a material which is right from the birth to the production and the implementation of the material, that is starting from 0 and reaching to the 100%, whereas operational energy it is again which needs 100% of maintenance and the cost and all these factors implemented in the operational energy, which is going down in a period of about 60 years. From 100% of operational energy, the building dies or the value goes down at an age of 60 years. So, not to be confused with life cycle costing. So, the financial cost of a building throughout of a lifetime can be calculated, which does not include the environmental criteria like external cost or cost to the society, capitation cost of the material, operation cost of the material, and maintaining this material, and how do we recycle this material and also dispose it in a proper way. It can be combined only with the LCA life cycle analysis of the building materials. The embodied energy reduction can be in a greater extent. Now, look at this simple graphical chart. Energies which is used in terms of transportations, that we look at it basically from the extraction of this material, that is from the natural resources of the materials, and processing the material like shaping the material to the required sizes, carrying from the site to processing it, and then manufacturing this material into a usable way. In here we can implement reusing the waste materials or recycling the materials to appropriate constructions, and these manufactured materials again it can be used and the end of the life of the material, the life value of the material and the final disposals. All these three things, processing, manufacturing and the end of the life, which includes reuse and recycling of the materials. And the energy, if you look at it, the waste heat which is generated during the processing and also towards the end of the life, we need to take it into the account. These are marked in the red, that means this energy which is produced and it cannot be reused or it cannot be conserved in a proper way. So, life cycle energy analysis students, please try to get into the proper flow chart of extraction, processing, manufacturing, use, end of life and final disposal. All these aspects into a consideration of about reuse and recycling. Now, assessment of these flow chart into materials and water. These energies which needs to be conserved in a proper way, and also in terms of generating the waste heat and the emissions of the toxic substances and the functional unit of the building. Look at the functional unit of the delivered energy, which results in terms of the energy analysis. It is always a unit which is measured in kilowatts, energy to heat in a home for a year, and also to build a nuclear power station or a wind turbine like renewable energies, and also the embodied energies. So, life cycle assessment of a materials, if you look at it, washing machine of 5 kg which runs over it, and packaging for a 1 liter milk, and disposable of a waste. So, 4 major stages which is involved in it: the goal and the scope, definition of this materials usages, and defining the purpose, and extending the study and the boundaries, and description of these materials and the functional unit, and also doing the inventory of the life cycle analysis, which includes the detailed compilation of environmental inputs and outputs for every stage of the life cycle, and which results in the long list of resources and also in the emissions in terms of incompatible units, which quantifies and aggregates the relative importance of all environmental burdens which is obtained during the life cycle analysis or life cycle impact assessment, which is interpreted in terms of the results, life cycle analysis of construction and demolition waste by EPSRC. If you look at it, the raw material which produces 1.05, and for during landfilling 0.56, and which comes into terms of reusage of this material, it is only 0.05 tons, which is considerably less, and the water usages in terms of liters, 352 liters, in terms of reuse, it is which is considerably a greater value of 17.64 liters can be reused or recycled. So, the primary energies we have looked at it, and global warming if you look at it 12.6, and which can be reduced by usage of reducing the carbon dioxide. Several aspects like visual noises also included in the graphical chart, and in terms of road transport, in terms of kilometer, which has a very lesser value. The land usages, if we look at it, landfilling is 8% score and reusage of the land is in 9%. That shows a positive approach in life cycle analysis of construction and demolition waste. So, we have seen here raw material, water, land, visual, noise, and also global warming and water and transport in this chart. So, already we have discussed about the energy and the waste heat which is produced during the extraction to the final disposition of the LCA analysis. So, the manufacturing, the main integration of energy and reusing this material, recycling the material and reducing the energy, that is cradle to grave, right from the birth of the material to the death of the material needs to be reused in a proper way. That shows the life cycle energy analysis. These are some of the graphical representations. From the site, it goes to the manufacturing companies, and from the manufacturing companies it goes to different places by means of transportation, either by road or either by water or either by air. The depth of the study, which includes direct inputs needed in the manufacturing process, like example, we can look at bricks which is used for a house. How much is the energy which is needed in terms of the manufacturing of the bricks? Second, inputs of this manufacturing machines in the product, and by producing the manufacturing the bricks. Energy used by the companies during the production of the bricks. Thirdly, for the machines, that is the operational energy used in the manufacturing of the bricks, which does not refer to the energy available, which refers to the energy recovered by burning a product, could be called as a cumulative energy demand, or else the sum of the energy which is inputted into the product systems. This is nothing but embodied energy. Embodied in generation is a electricity generation which is connected to a distribution network rather than to a high voltage national grid. In general, it includes the manufacturing process of a product which goes through it. From the higher embodied energy value will have. For example, if you look at it, timber board materials have much higher embodied energy than the equivalent saw size of a timber. The energy embodied in a new construction and renovation, which is in each and every year, according to UK, it accounts for 10% and 50% in the manufacturing of the materials and 50% used in the transportations. The energy which is used in the production, which is 50%, and energy which is used only for transportation, again it comes under the 50%. It is a great value, and also it is surprising. The electricity which is delivered to the site and the losses in terms of the production, like fuel conversion of the power plant, nearly 60 to 70% of the primary fuel can be only utilized, other 40% to 30% it goes as a waste. And transmission, and this is something called distribution losses, they call it as in the electrical emissions. It comes under the value of about 2 to 8% generally in terms of production. Fuel extraction processes and the delivery of these materials, which can be consumed in use in power plants, transport, equipment and industrial plants. Processing the heat, transporting the materials and fuel used in the situation which is not directly to oxidize, such as oil and gases in plastic containers or carbon in cokes and so on. Energy in terms of capital equipment for our countries. The embodied energy for a concrete, which results in 11 kilowatts per kilowatts hour for ton. Gypsum, bricks is 60 and 470 in Netherlands. Plastics, which gives a higher value. And glass comes around 528, bitumen and paint comes around 278 and 667. By various process, how much is the energy can be taken into account of an embodied energy, it is given in the graphs. So, 3 different sources, one is we have seen from Danish, another one is from the Netherlands, another one is from Syria. So, if you look at the differences, it is between Danish and Netherlands, it is a slighter value 11 to 17, 834 to 473 or 144 to 306, whereas here in by the Syria, that is like by the impact assessment methods, it reduces the embodied energy in a greater extent. All these life cycle analysis and the cost models for the building construction which is developed, that is from cradle to grave, the mantra for the embodied energy and also for the life cycle assessment, environmental impact, energy cost, the raw material acquisitions, product manufacturing and the transportations, which again involves the every material which involves the environmental impact and also the cost of the material and also the energy which is used in the production of the material. construction and the fitting, operation and the maintenance of the building, renovation and the demolition of the building, that is grave, that is the death of the building. It includes the operational energy and energy cost. From raw material, it includes only the energy cost and the environmental impact. From raw material, product manufacturing, construction, operational energy only differs by operational energy and the energy which is required and costing which is required for the renovation of the building or the demolition of the building. This is the graphs which represent or demonstrates the whole building life cycle analysis and also the embodied energies. Inputs like if you look at it, some broken glasses which is used in the factories or recycled in the factories for various manufacturing, some X percentage, and look at the value which is used in terms of melting the raw material with the amount of recycling. So, the material 1, it is like from 100 percentage it goes to a value of about 90 to 93, and other material 2, material 4 if you look at it, it is goes down to 100 to an extent of about 60 percentage, that is a percentage of recycling value. Energy and economic evaluation of the building integrated by renewable energy, like if we use the photovoltaic systems. So, we can consume the energy and we can conserve this energy and we can consume it in a fruitful manner. So, various recent studies are going on now in terms of energy payback systems and increasing the lifetime of the PV integrated systems. So, this study is something like which gives an idea for us to know about the centralized PV, or we can have only electricity mixed PV or building integrated PV, PIPV they will call. Energy and economic evaluation of this building integrated photovoltaics and the methodology, the functional unit, comparison cost and energy analysis, and average GU mix, central PV and the BIPV. BIPV is nothing but building integrated photovoltaic systems which generates the electricity and also displaces the conventional energy which is required for a building, and it provides a weatherproofing and displacing the conventional cladding systems. The various values, central PV if you use it, or BIPV if you use it, or net BIPV. They look at the differences in terms of kilojoules, 4.2, 2.9 and 2.9, and net energy balance if we look at it. At 68 percentage it gives the energy payback, or 7.9 percentage we can get it as in terms of energy payback. BIPV we can look at it is 5.5 or 4.8. So, the more recommended is energy payback if you look at it, it is central PV. Or net energy balance, the remaining energy balance if you look at it, net BIPV is a great, plays a major role, it has 81 percentage. If you look at the energy saving, it remains same for all the systems, 13.2 it remains. In terms of investment cost, if you look at it, net BIPV is expensive, but if we look at the net energy balance, this is giving back the returns in a higher value. Calculating this unit electricity cost for PV systems. So, buyback price is 67 and 75 and 36 years. Capital cost, it's BIPV is plays a higher value here, and other things it remains more or less similar. The summary of the L cycle analysis and the embodied energy, which recommends the usage of renewable energy systems and reduce the energy consumptions, and various methods and systems which is integrated in the PV system we have seen in this embodied energy analysis. I repeat, the life cycle analysis and life cycle cost models which is used in the building constructions. So, building life cycle. Building life cycle in a shorter way, people used to call it as a cradle to grave. Cradle to grave is right from the birth of the material. The birth of the material is the extraction of the resources, quarrying from the site and dressing from the site, and according to the shapes and various sizes which is required in the building industries, and transportation of these materials to the site, and mixing the various material combination in terms of requiring strength, either in terms of masonry constructions or reinforced cement concrete constructions. So, all these things, the birth of the material, either it is a natural resources material or it is a which is man-made resource material like cement and various aggregates used in the building industries, everything comes under in terms of raw material acquisition, which is used in terms of foundations, that is something like substructure to the superstructure, right from the excavation of the soil in the foundation and towards the completion of the building, everything in the life cycle analysis, it is called as a raw material acquisitions and the environmental impact. While we depleting these natural resources from the site, the energy which is used in terms of the production of this material, and also it includes a cost in terms of manufacturing these materials, everything makes a vital role in the LCA and the embodied energy. So, product once it is out from the site, it goes into the companies, that is nothing but the manufacturing unit. In the manufacturing unit, these materials like processed in a greater manner, for example, glasses, silica particles are all can be processed in terms of manufacturing of the glasses. Various types of glasses can be produced in terms of the usages, and again these materials need to be transported to the site for the constructions, which again involves in terms of environmental impact and energy and the cost of the materials. And construction of this fitting of these materials from walls, doors, windows and roofs for ceiling, and also various furnitures, all these indoor and outdoor elements and interiors of the materials used in the buildings, everything which has energy and costing, that is nothing but the completion of the building materials in the building, right from the construction of the superstructure to the substructure, and also the operation and the maintenance. Here it comes the HVAC systems like heating, ventilation and air conditioning, that is nothing but to operate the building we require some amount of electrical energy, some amount of renewable energy, some amount of energy waste, that is in terms of operating this energy, and also the cost of these energies used in the buildings also it is taken into the account, and environmental impact by consuming the energy from the public resources, or the environmental impact of using these non-renewable energy materials in the buildings, and the renovations. After we all knew that over a period of 60 years, the building, any type of building which requires some amount of maintenance, and also the renovation and demolition of the building, whether it need to be renovated in a proper way or it can be demolished and it can be rebuilt it again, everything includes the signage of death of the building. Again, if you look at it, it is environmental impact and energy and cost of the material. See, these are various impacts incurred by a building throughout its life cycle. It can be a smaller residences, or it can be a office building, it can be a environmental recreational buildings, it can be any building in the constructions, but it includes all the process of environmental cost and environmental impact and energy and cost wastages is there associated with the cradle to grave. Here we have seen about building life cycle from cradle to grave and the models which is associated in the building constructions. I repeat, energy requirement for melting raw material with different amounts of recycling. So, look at this graph in y axis, it gives the value of amount of energy which is required and amount of energy which is recycled. So, the x axis it gives the value like from 0 to 60 and from y axis it gives starting from the range of about 50 to 100. So, 100% value in terms of melting the raw material in terms of recycling. So, the first material 1 if you look at it, it is material 1 is here, it is shown in a green color. So, it leads from 100 to 80, somewhere around 75 to 76 is the value. The material 2 is just indicated in the blue color, it is 100 to again 85, and in a cyan if you look at it, that is a material 3 from starting from the range of about 100, again it goes into a range of about 79, and material 4 which from 100% which goes down to the value of 50. These are various energy requirements in terms of melting the raw material with different amounts of recycling. The most prescribed one is the material 1 because which requires 85 to 90% the material can be recycled and can be used in the buildings. The material which has a value of ranges between 50 to 60% is not advisable or not recommended for the usage of LCA and the embodied energy in a renovation of the buildings. Thank you.